Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about the module X-ray photoelectron spectroscopy part 2, coming under the topic surface morphology from the paper Characterization Techniques for Materials 2. From this module, students may get to know about the following: the peak identification, chemical shift and quantitative analysis of X-ray photoelectron spectroscopy. Also, the depth profile of X-ray spectrum will be discussed. The X-ray photoelectron spectroscopy counts the number of electrons ejected from the materials when X-ray is irradiated on the surface. The XPS spectrum represents the number of electrons recorded in certain range of energies. This XPS is a powerful tool for chemical analysis at the surface of the specified material. It identifies the presence of elements in the layer within several nanometers from the surface. Importantly, the positions of peaks in the XPS spectra are sensitive to their chemical compositions. For example, carbon peak positions in carbon dioxide are different from those in saturated hydrocarbons. This phenomenon is represented as chemical shift in XPS spectra and provides extra information for chemical analysis. Also, XPS instruments are able to generate depth profiles of the chemistry of the surface layer through the bulk material and reveal the spatial distribution of elements on the surface and inside layers of the bulk material. The XPS spectra are quantified in terms of peak positions and peak intensities. The peak position indicates the elemental and chemical composition, and peak intensities measure quantity of materials at the surface. Other values such as full width half maxima are useful indicator of chemical state changes and physical influence. This module focuses on the qualitative and quantitative analysis of XPS spectrum. So, the spectrum analysis, the XPS spectra is analyzed by identifying the peak and locating the shift in peak positions due to presence of elemental compositions. Let us see how the peak identification is taking place in XPS spectra. The binding energies of various core level electrons for peak identification in XPS spectra are tabulated in the reference section of this module. These energies are the primary source for identifying the presence of elemental components. The peak identification in XPS spectra, however, are more complicated because Auger peaks may be present. We use two different X-ray sources to distinguish the Auger peaks from the photoelectron peaks. An Auger peak represents the kinetic energy of an Auger electron that changes with energy of primary X-rays. Thus, an Auger peak will shift in apparent binding energy in an XPS spectrum when we change the X-ray source. For example, an Auger peak shifts by 233 electron volt in the XPS spectrum when we change the radiation from manganese K alpha of 1253.6 electron volt to aluminum K alpha line with energies of 1486.6 electron volt. The peak positions in the X-ray spectrum are likely to be affected by spectrometer conditions and the sample surface. Before XPS peak identification, we need to calibrate the binding energy. This calibration is particularly important for samples with poor electrical conductivity. The calibration can be done with an internal standard, that is a peak showing little or no chemical shift, as an example of elemental silicon. The most common method is the use of carbon 1s peak at 285 electron volt appearing from the carbon adsorbed on the surface of the sample. The carbon from organic debris as C single bond H or C single bond C in air is found on all samples exposed to the environmental conditions. The peaks of core level binding energies as listed in the table in the reference section again attached with the module and are sufficiently unique for element identification. The binding energy increases with the degree of oxidation. The binding energy of aluminum atom is different in different chemical environment. The binding energy for pure aluminum metal is around 72 to 73 electron volt, and for aluminum oxide it is 74 to 75 electron volt. The chemical shifts. Chemical shifts of binding energy peaks for an element are caused by the surrounding chemical states of the element. Knowledge of the possible chemical shifts is necessary to identify the peaks accurately. We can use the features of the chemical shifts to identify the elements and chemical compounds. For example, Figure 1 shows the XPS spectrum of polyvinyl trifluoroacetate, termed as PVTFA. The carbon atoms in different environments generate distinctive peaks as shown in Figure 1a. Similarly, oxygen atoms in two different environments generate distinctive peaks as shown in Figure 1a. Similarly, oxygen atoms in two different environments also generate two peaks as shown in Figure 1b. The XPS spectra shown in Figure 1 with defined peak positions and relative peak intensities can also be used as a fingerprint to identify PVTFA. The small shifts in binding energy is caused peak overlap as shown in Figure 1b. Hence, we might need to carefully resolve the overlapped peaks with assistance from other computer software. The chemical shifts of the C1s peak are summarized in Figure 2. The range of the C1s shift extends over 12 electron volt. Quantifying the amount of chemical shifts in the spectrum can identify different carbon bonds. The binding energy difference between CC and CO is about 3 electron volt. This is extremely useful for identifying polymers by revealing various carbon bonds. Also, the chemical shifts reveal the degree of oxidation in molecular solids. Higher chemical shifts occur for larger number of electrons transferred. Chemical shifts decrease with increasing atomic number and suggest less possibility in metallic and semiconducting elements. For example, the shift range for silicon 2p is less than 6 electron volt. Chemical shifts also occur in Auger spectroscopy spectra. and the chemical shifts can be significantly larger than the shifts in XPS. For example, the shift between metallic and oxide aluminum peaks in aluminum Kl2p is more than 5 electron volt, and the corresponding shift for aluminum 2p in XPS binding energy is only about 1 electron volt. Issues with insulating materials. The peak positions in XPS spectra for insulating materials do not agree well with the standards provided in handbooks. To understand this phenomenon, let us start with the basic equation for binding energy calculation as Ek is equal to h nu minus Eb minus phi, where phi is the work function of the material and represents the energy required for an electron to escape from the surface of the material. H is the Planck's constant and nu is the frequency. When a conducting material is electrically contacted to a spectrometer, in equation above, a work function of the spectrometer and its value is constant. However, for an insulating sample, it is not certain and is related to the surface potential of the material. Photoemission from an insulating material builds up positive charges on the surface of the sample. This build-up changes the surface potential of the material during XPS data acquisition. In insulating materials, the incident electrons cannot be removed by electrical conduction, leading to charge the surface negatively in AES. Change of surface potential makes the kinetic energy or binding energy measured tens of electron volt different from the standard value mentioned in the published tables. The charge neutralization method is used to resolve the surface potential issues by providing stable and uniform surface potential on solids. In XPS, the surface of the material is provided with flux of low energy electrons using electron gun as shown in figure 3. The electron flux compensates charge loss due to photoelectrons that are escaping from the surface. The flux helps maintaining stable surface potential. Performing XPS in insulating materials, the surface charge issue is prominent with monochromatic compared with non-monochromatic X-ray radiation, because the non-monochromatic X-rays illuminate the window of the X-ray gun as well as other surfaces inside the vacuum chamber, producing sufficient secondary electron flux to neutralize the positively charged surface of the material. Hence, uses of non-monochromatic X-rays has the identical effect as using an electron gun. Let us see how to analyze little quantitatively the peaks and the sensitivity factors. The quantitative elemental analysis in X-ray spectroscopy is identical to the electron spectroscopy. This quantifies the concentration of chemical elements of the sample measured from the peak intensities of the spectrum. Most of the parameters required for quantification of the atomic fractions of elements from the intensity of electron signals in both XPS and AES are not known, and the following empirical equation is generally used, which is Xi is equal to II divided by Si whole divided by sum over Ij divided by Sj. where Xi is the atomic fraction of a surface element, Ii is the peak intensity, and Sj is the sensitive factor. The Sj for each element is experimentally determined and varies with conditions of the instrument and sample surface. It is desirable to measure the sensitivity factor for a given spectrometer and for a specific sample type. Generally, the sensitivity factors are used from table of handbooks with certain corrections according to the instrument characteristics due to its difficulty in compiling all the sensitivity factors. The quantitative calculations using these Xi values has assumed and approximated. The intensity of XPS peaks can be calculated from the peak areas after nullifying the background. Sensitivity factors are varied for different materials and for considering developments in instruments. For example, the chemical contamination on the surface of the sample affects the accuracy of this calculation Xi. The composition depth profile. The compositional change with position in the material can be understood by measuring the depth profile XPS starting from the surface plane. The XPS is a surface sensitive technique. A depth profile XPS for materials can be recorded by combining a sequence of ion gun etching steps with XPS measurements starting from the top surface. An ion gun is used to etch the material for a period of time and XPS spectra are acquired. After each ion gun etch, the material exposes a new surface and the XPS spectra is recorded and provides elemental details for analyzing the composition of these newly etched surfaces. Generally, the depth profile of composition is determined using spotted depth profiling using an ion gun. The ion gun provides a flux of positively charged argon ions with current density of 1 to 50 microamps per millimeter square and energy of 0.5 to 5 kiloelectron volt. The ion beams bombard a surface, causing it to eject atoms from the surface. The schematic of the depth profile experiment are sketched in figure 4. The material is dug for different depths of D1, D2, D3 and D4 as shown in figure 4. A set of XPS spectra corresponding to the O1s peaks of titanium oxide is displayed in figure 5. The objective of the experiment is to observe the trend in the elemental quantification values as a function of etch time. The actual depth for each XPS analysis is dependent on the etch rate of the material being etched by ion gun at any given depth. For example, the data in figure 5 derives from a multi-layer sample consisting of alternating layers of silicon oxide and titanium oxide on top of a silicon substrate. In another example, figure 6 ABC provides information of the XPS spectra of C1s at various depth positions of D1, D2 and D3, where D1 is less than D2 is less than D3 performed for a graphene oxide coated indium tin oxide layers. Here, the appearance of peaks at binding energy 284.8 electron volt is assigned to C1s core level. In addition, at the graphene oxide surface, all the structures show a hump at energy equivalents of 286.8 electron volt and 288.6 electron volt that corresponds to CO and C double bond O respectively. The intensities of the C1s peak decreases and the peak corresponding to the C single bond O vanishes as digging depths are increased to D2 and D3 within the geolayers. In figure 6, D, E and F, the peak at binding energy of 530.1 electron volt is assigned to the 0,1s, erase O1s core level of the oxygen for all the structures. At the surface of graphene oxide, a hump is observed at binding energy of 532.3 electron volt, indicates the presence of C single bond O bonding. A prominent increase in the intensity of O1s peak and diminishing of C single bond O peak is observed with further removal of oxygen from the graphene oxide surface layers towards the depth of the thickened layer. Quantitative analysis of a depth profile, in addition to quantify concentrations, requires accurate measurements. There are several factors for resolution of issues raised in depth measurements. First, the etching rate for each type of atom is not constant even though the ion beam energy and ion density are exactly the same. The consequence of this phenomenon is that the preferential etching occurs in samples containing multiple elements. In samples comprising several elements which are not uniformly distributed, certain areas are etched faster than other areas because of preferential etching. This results a rough crater surface generated with increasing depth of etching. The depth scale of the profile is based on the average etching rates. Thus, the measured concentration of elements with higher etching rates or higher sputter yield will be higher than the real concentration. Second, the incident ions can smear the interface in the depth profile. Figure 7 schematically illustrates the interface smearing during depth profiling. This is also the case shown in figure 8, in which the smooth interface coating and titanium substrate becomes diffuse in the profile. The main reason for interface smearing is that the incident ions produce coating of atoms and or substrate atoms to cross the interface. The atom displacements caused by the ion bombardment could be understood considering the energy brought into the sample by the ions. So students, let us summarize what we have learned in this module. The introduction, qualitative analysis of XPS spectrum has been discussed. The peak identification, chemical shift in XPS spectrum and issues with insulating materials are discussed with schematic diagram. The quantitative analysis of XPS and sensitivity calculation has been discussed, and the possibility of the depth profile in XPS samples are also studied. Thank you.